Hello and welcome. Today, we are diving into a really fascinating story from the world of quantum computing. It's a story that honestly starts out looking like a complete and total failure, but ends up being this massive success. And it all comes down to one very confusing number, 0.78%.
So, here's the central mystery, the big question we're going to unpack. How can a system with what looks like a 50% error rate, basically a coin flip, be hailed as some kind of breakthrough? You'd think that's a disaster, right? Well, that's what everyone thought at first. But the real story here is so much cooler. All right, let's get right into it. We're going to start by looking at the raw data, the numbers that caused all this confusion. This is where that 50% error paradox really begins.
So check this out. These are the actual results from over 1,000 runs of a quantum simulation. You can see we got four possible outcomes. 10 popped up 528 times, and 00 showed up 488 times. The other two, 01 and 11, are, well, they're super rare. Now, if you're just looking at this, you'd probably think, okay, 10 is the right answer. It came up the most.
And that's where the trouble starts. If you assume that 10 is the only correct answer, then all those other results are errors. So you've got the 488 counts for 00 as a massive error. You add in the few others and you get this absolutely staggering error rate of 48.4%. That's basically a coin flip. It makes the system look completely broken.
But, and this is where it gets really brilliant, the problem wasn't the system. Nope, the problem was our assumption. To solve this whole paradox, we have to totally rethink what we even mean by a right answer.
This right here is the key. You have to ask, what if the problem isn't the errors at all, but how we're defining correct? I mean, we're talking about quantum mechanics, where things can be in multiple states at once, right? That whole superposition thing. So what if the algorithm was supposed to give us both 00 and 10? And that brings us to this really cool concept, a procedural success condition. In this way of thinking, success isn't about hitting a single target, a single bullseye. It's about the algorithm producing a specific pattern of outcomes. The goal was never just 10. The goal was a mix of 00 and 10. So let's look at that data again, but with this new idea in mind. See? Now, both 00 and 10 are labeled as correct. They were the intended result of the whole simulation. All of a sudden, what looked like a massive failure is starting to look like an incredible success. The only real errors are the ones that were never part of the plan. And what are those errors? Well, it's just that one lonely count for a 1 and the 7 counts for 11. That is it. A grand total of just 8 mistakes out of more than 1,000 tries. You can see how this completely flips the script. And when you do the math on those 8 little errors out of 1,024 total shots, you get the true unmitigated error rate. And here it is, 0.78%. It's incredible. We've gone from a 50% disaster to a sub 1% triumph just by understanding what the algorithm was actually trying to do. Okay, so we've solved the mystery of the number, but that just leads to another question. How on earth does the system get such a low error rate? Well, the answer lies in this really radical software-first approach to dealing with quantum noise. This slide really highlights the philosophical difference here. You see, most of the quantum industry is in this huge hardware race, trying to build physically perfect, noise-free qubits. This approach, it's completely different. It basically says, look, noise is going to happen. It's inevitable. So instead of trying to prevent it, they model it in the software and then just subtract it out of the final answer. This visual gives you a great way to think about it. The system is doing two things at once. On one hand, you have the multiversal state tensor. Think of that as the perfect, pure, ideal signal. At the exact same time, you have the decoherence tensor. You can almost think of this part like a pair of noise-canceling headphones, building a super precise model of all the interference and chatter going on. So it all boils down to this elegant three-step process. First, the core engine simulates the perfect, ideal state. Second, while it's doing that, it's also building a model of all the noise it expects to see. And finally, and this is the magic trick, an algorithm called decoherence subtraction just removes that noise model from the final result, leaving behind this beautifully clean answer. This quote just sums up the whole strategy perfectly. It's called the sovereign execution protocol. You don't fight a head-on battle with noise. That's a losing game. It's more like an algorithmic judo move.
You learn the noise, you model it, and then you just remove it.
So this specialized solver is obviously incredibly good at what it does, getting that amazing 0.78% error rate. But the ultimate goal is way bigger. And you guessed it, it comes with a brand new, really tough challenge.
So right now, this system is a master of solving very specific kinds of problems. But the holy grail, the ultimate goal, is to turn it from a specialized tool into a true universal quantum computer, a machine that can solve any problem you throw at it.
And this lays out the new battlefield perfectly. On the left, you've got our hero, the stable solver with its tiny 0.78% error. But on the right, that's the next mountain to climb. The very first attempt at creating a universal T-gate, which is a key building block for a general-purpose quantum computer, results in a massive 15% logical error. And this isn't physical noise anymore. This is information actually being lost by the new algorithm itself. So, how do you even begin to tackle a 15% error rate? Well, you do it with a really careful 3-phase engineering plan. First is Crucible, where the whole goal is to go back to the drawing board and design a better T-gate algorithm, one that's just more efficient and less leaky. Second, in Coherence Filter, they'll test this new gate in a totally safe way, on a read-only copy of the main engine. And then finally, in Sovereign Coupling, the fully tested, fully vetted universal gates get integrated into the life system for real. And that really brings us to our final big picture question. The whole quantum field is watching this fork in the road. Is the future going to be won by the people building physically perfect, insanely expensive hardware? Or can a really clever software-first approach, one that literally embraces noise and just subtracts it away, outmaneuver everyone else and solve the final grand challenges of quantum computing? We'll have to wait and see.